This session is going to focus on advanced data analytics for hyper-local air pollution action, where we will explore cutting-edge techniques to analyze and address issues at the community and ground level. For this session, we have Dr. Nidhi Malik, who's a consultant at the Air Quality Sector CSTEP. She'll be chairing the session. As panelists, we have Professor Dan, who's a research professor. He took the session in the morning as well. Dr. Neerav Lekhinwala, who's a senior associate at the Air Quality Sector. Mr. Mrinmoy Chakrabarti, he's a PhD candidate at the University of British Columbia. And Dr. Satish Swaminathan, who's a postdoctoral fellow at the Columbia University. Dr. Nidhi Malik is a consultant at the Atmospheric Composition Observations Group at CSTEP. She holds a PhD in air pollution from IIT Dhanbad and has completed her master's in environment management from GGS's Indraprasth University, New Delhi. Before joining CSTEP, she has worked as a trainee engineer at the Delhi Pollution Control Committee and also has been a research associate at NAM Science and Technology Center at Indian Habitat Center, again at New Delhi. I would now request her to please take the session forward and introduce the panelists.
Thank you for the warm introduction, Anshika. Good afternoon, everyone. I'm Nidhi, and I welcome you to our session, Advanced Data Analytics for Hyperlocal Air Pollution Action. Today's presentations will showcase how advanced analytics is being applied to model and monitor air pollution, opening up new possibilities for cleaner air and healthier lives. So let's dive into the power of data and its role in transforming our approach to air quality management. For today's session, our first speaker is Professor Daniel Westervelt. He will present 3 examples of advanced data analytics for hyperlocal air pollution. I'll introduce. Come, please come. Yeah. So he's an associate professor at LDEO and is also an affiliate faculty member of Columbia University Data Science Institute and an affiliated scientist with NASA Goddard Institute for Space Studies and Air Pollution Advisor to US Department. His current research spans from air quality and climate modeling to deployment and calibration of low-cost sensors for air quality. And prior to his faculty position at LDEO, he worked as an associate research scientist there and as a science, technology, and environmental policy postdoctoral research associate at Princeton University. Now I welcome Professor Daniel to take on.
All right, perfect, yeah. All right, yep, so it's me again. So I'll talk about a few different examples of some advanced data analytics that we're using for air pollution studies. And hopefully everybody had a good lunch and you're not too tired from lunch, but I'll try to keep your attention going here. So I first just want to acknowledge my team members who several of them are in the room and a lot of them have contributed to this work. So you'll be hearing about some of their research. That QR code is our group website if you want to find out more about us, and those are some of our funding sources. So I said 3 applications of advanced data analytics for air sensor research, and the first one maybe isn't really that advanced because it's mostly just linear regression, but we're going to go with advanced anyway for it. And so we'll be talking about regression models to bias correct air sensors towards reference data quality. So kind of on the same theme of what was being discussed this morning. I'll try to go through that pretty quickly since we've all heard enough about that for now. The second example will be machine learning methods to attribute sources of pollution using gas and particle sensor data. And then the third one will be data fusion of satellite and sensor data to obtain high spatiotemporal resolution PM2.5 data in especially data sparse regions. So yeah, we talked about correction and calibration models. The simplest form of these is a linear regression, and it's been widely used with a lot of success. I take this figure from a paper by Carl Mallings, which is a really nice figure. where they plotted on the y-axis on the left the manufacturer reported PM 2.5 from a purple air, and on the x-axis a reference monitor PM 2.5. This was in Pittsburgh, and they colored it by relative humidity, and you can see that there's a lot of bias in the data, a lot of deviation from the one-to-one line at high humidity. But if you apply this correction factor with this linear calibration model, which is, all right, don't worry about the pointer, which is shown in the bullet points there, you can get some pretty accurate data. So we've been over this before. We did this in Ghana early on, and really this work was led and spearheaded by Garima, who you heard from earlier. She did a lot of this data analysis, and so she was really a key part in this story of the Sensor Evaluation Center. But we started off with just a 3-sensor intercomparison where we just used 3 common US manufacturers: Clarity, Purple Air, and Modulaire. And we got some results here basically showing the agreement. So these lines that you see on the scatter plot are the one-to-one lines, and you can see that there is some differences between how close these data perform, these sensors perform based on which vendor they're from, basically. So I think it was pointed out earlier today also that one of the key points that we should think about is not just evaluating sensors and developing correction factors. That's a fun exercise, but does it really move the needle? What we want to do is then apply that data to large networks. And in this project that also Garima was working on, we applied this correction factor that we developed from these Clarity nodes and applied it to a network of about 18 PM 2.5 monitors throughout Accra, Ghana. So this is one of the first citywide estimates of air quality in Accra, Ghana. And you can find more in the paper that she wrote, which was published last year. We've also, just to point out, we've done this in some other places as well. This is back home in New York City. This is a slightly different way of showing the data. So here I'm showing a time series where the blue is the raw purple air data, and the yellow is the reference monitor data. So this is the FEM data. And then if we do, again, a multiple linear regression correction factor, you get the red line, which is much, much closer to the FEM or FRM data. So a highly accurate, corrected purple air data set. So we're starting to do this at our lab at Columbia. Based on this morning's discussion, I think I need to use a CET acronym for this. I haven't really figured out one yet, but maybe Columbia CET would be one to think about. It turns out that the sensor evaluation thing is a good idea, so congrats to Mike and Allison for doing that. But we have a GRIM EDM reference monitor, which is shown there on the right, and then we have about 10 or 11 air sensor from different manufacturers that we compare against our GRIM. And we even have some kind of homemade air sensors that Teddy and Trevor have been building and working on. Trevor even has a demo of one that he brought with him here, so you can find him and take a look at it later. We don't actually have any results yet because this is very new. This Sensor Evaluation Center basically started this summer. So we've applied this methodology across many data sparse areas. I don't have time to go into all of them, but most of them have been in Africa, and then through Faye McNeil and also Sandhya, we have done it in one site in India, and you can see Sandhya's poster later today. But just to give you an example of the places that we've done this, I think many of you were at the training yesterday where Garima was doing the comparison of reference data and low-cost sensor data in Ouagadougou, and that data is actually from a paper that's still in peer review. So you were getting some really recent, fresh off the grill type data. The next step that I think that we want to try to push sensors for, or one of the next steps would be to try to attribute sources. And so we had a multi-pollutant air quality monitoring setup in Kinshasa, DR Congo, which is a city of about 16 million people. It's very large. And we were going to try to use this data to attribute sources of pollution. So to do that, we use this non-negative matrix factorization method. I think for those that are familiar with source apportionment, you probably have heard of positive matrix factorization. It's essentially the same thing with a few minor differences. But what it does is factors the original data set, the time series of PM2.5 and gases into a linear combination of matrices. And one of those matrices basically gives you a factor composition. So it tells you, you get these interpretable factors that you can try to assign to sources. It'll tell you how much each gas or each particle bin size contributes to that factor. And so that information can be used to sort of make some educated guesses about what the sources are. And so this would be a pretty low-cost method for source apportionment. You can buy a multi-pollutant air monitor. We'd used the one from QuantAQ. It was about $5,000 US. And these are kind of the results we got. So we found 3 distinct factors, and their factor composition is shown here on the panel. So we found a factor that was carbon monoxide dominated and also dominated by the influence of larger particles. So we kind of attributed that to local combustion vehicles and cooking, most likely from secondary particles, because these particles were a bit larger. We used the AlphaSense OPC, which gives you the size distribution of particles, to be able to diagnose that. The next factor was probably more likely to be primary particles from combustion as well, so black carbon from small fires, cooking, et cetera. And then a third factor was completely different than the other and had a unique diurnal profile and was indicative of regional sources, probably biomass burning, which is a big source of pollution in that area. We can also use wind data to help discern sources. So the multi-pollutant monitor also had a wind speed and wind direction sensor, and that can also help us figure out, okay, is this factor regional sources or is it local sources? If it's associated with slower wind speeds, then it's more likely to be local sources. My last area here will be the role for air sensors for satellite data fusion. So there's a big problem with using satellite data for air quality, and that is that they measure the entire atmospheric column instead of the ground. What we care about is the breathing level height pollution. So there's a couple of different solutions you can use to deal with that. You can use a geophysical model to convert the AOD to the surface PM2.5, and Randall Martin's group has published 1 billion papers on that, and you probably could find them online. But another solution that I think is really interesting that is gaining traction is using statistical models to develop an empirical relationship between PM2.5 and column AOD. And so that's what we're doing here. And we're doing it specifically in a region that traditionally does not have a lot of data available. So these kind of approaches are very common in the north, but people have been hesitant to do them in places like Africa because you do need a lot of ground-based data in order to validate the model and to build a good model that can convert that column data into surface. So we found that with all of the monitoring that's been going on in my group and in AfriCARE and AfriSet and all of the various groups, there is starting to be enough data locally to do this. And so we basically train a machine learning model that compares the satellite AOD and a few other factors to the surface data. And then we can sort of take that relationship and apply that everywhere. By everywhere, I mean sort of spatially within like a region like West Africa. And then what the result is sort of a highly spatially, temporally resolved, gridded data set. So we can get it down to, right now, to about 1 kilometer by 1 kilometer resolution, which is, not exactly neighborhood scale, but it's sub-city scale. It's within, you can have different areas within like a city. So that could be applicable to like epidemiology studies and other studies like that. This is some of the initial results here. We have the predicted machine learning PM2.5 versus observations. The machine learning is the observations are in blue and the machine learning is in orange and a couple of other colors as well. So we used multiple models here, but the take-home point is that the machine learning models do pretty well compared to independent observations. And these are different cities in West Africa where we've actually been able to validate the model. And we have high R-squareds of about 0.9 and mean absolute errors about less than 10 micrograms per meter cubed. I think in the interest of time, I'll keep going here, but this is sort of looking at the same data just as scatter plots. And one thing that's really cool is that you can actually, if you trust that the relationship between AOD and PM2.5 is relatively stationary over time, which we can talk about that, but that might be a little bit of a stretch, but we're gonna go with it anyway. If you trust that, then you can actually get a historical PM2.5 data set in places that never had PM2.5 on the surface until 3 years ago or something like that. And so we did this in Burkina Faso, where we have, using this method to estimate PM2.5 since the beginning of the satellite record, which for AOD and MODIS was about the year 2000. All right, so you can see in Burkina Faso, we found an increasing trend of PM2.5 over recent years, since going back to 2000 to present day based on using this method. Yeah, and it also makes for a really nice spatial plot. So this is the 1 kilometer squared spatial resolution over West Africa. You can get really high resolution data, and then you can apply this data to various studies like epidemiological studies, global burden of disease studies, policy studies, and so on. So yeah, that's my talk, and I think I'll just leave my summary slides up here, and happy to take questions. Thank you.
So if you could add, I don't know, if you could add an additional measurement when you're trying to do the source apportionment, like you were showing for Kinshasa, like what would you want to add? If you had $5,000 to add something to these low-cost sensors.
I mean, for $5,000, I forget how much a micro F black carbon monitor is, but something like that maybe. Yeah, I think, yeah, black carbon would work, or even being able to validate the gas sensor data would probably be a help too. That's not always feasible in resource limited settings. You know, we do have like BAMs in some cases, but we definitely like pretty rarely will have NO2 analyzers or CO analyzers or stuff like that. So that's a little more than $5,000, but I guess that's the gist.
Hi, it's a nice talk. So I just wish to ask one question. Like the relationship between, let's say, particulate matter and AOD is also having a special disagreement. Sometimes like different spaces having a different relationship they show. So setting up this kind of model where we want to create a historical PM2.5 using AOD, whether we also need to take care of the regional heterogeneity while developing this model, because over its particular, let's say India, the PM2.5 and AOD relationship varies between different geographies. So how to take care of those biases?
I mean, that's a good point. I think it's an important caveat of this work. Like we're taking the AOD PM2.5 relationship at individual points and trying to, I guess you could say, extrapolate that across a spatial domain. I think the idea is that we have to have as many data points as possible to limit the damage that extrapolation could do. That's probably the strategy, and that's why all these groups are here to, or one of the reasons why people are here to put sensors on the ground is to help do that. But I should also say that I didn't go into this, but the model also considers a bunch of other factors as well besides just AOD. So we consider a few of the gas phase monitored satellite products like Tropomi, NO2, and CO. We also consider a few meteorological parameters like humidity, temperature, because we know those are related to air pollution levels as well.
Thank you.
Yeah, hello, Dan. Thanks for a good talk. We all know the limitations of the satellite AOD, as you pointed out, and also the limitations of deploying this low-cost sensor measure. Does that mean the data fusion is the solution you are proposing now? And is it also a signal that we should be careful with correcting for the low-cost sensor data? And then also maybe you could indicate what is the anticipated limitations of the data fusion that you are proposing now.
Yeah, I mean, you spoke to basically two different applications of air sensors and satellite data. One of the big, I think, caveats that I also didn't get into is that we can't have high time resolution data. The best we could do is probably daily. If you want like hourly data from this satellite method, you're basically out of luck with this current setup. Now there's an approach, there's geostationary satellites that are starting to get hourly observations of things like AOD and NO2, and so as those become more available, I think that we could increase the time resolution. Right now, the geostationary satellites are only available in the north, and there's not, for example, one in Africa. But yeah, I think the use of satellites for correcting low-cost sensors is also pretty interesting. Mike Giordano, who has a paper on that that's in review right now, where he's used MERA-2 composition data to correct PM low-cost sensor data through I think a few cities in Africa. Yeah, so I guess that's what I'd say.
We will take the remaining questions at the end of the session. So thank you, Dr. Now I'll welcome our next speaker, Dr. Nirav Lekinwala. He will be presenting calibrating low-cost sensors and discussing their merits and demerits of calibration methods. Dr. Nirav Lekinwala is a senior associate in atmospheric composition observations group at CSTEP. He completed his PhD in air pollution source apportionment from Department of Chemical Engineering from IIT Bombay, and before joining as a senior associate, he worked as a consultant at CSTEP, and his areas of interest include air quality source apportionment using data-driven techniques to assess the impacts on health and also on low-cost sensors. So I welcome Dr. Nirav Lekinwala now.
Thanks, Sindhi. So I'll start. So the title for my presentation is Calibrating Low-Cost Sensors, and what I'll be discussing is we have tried at CSTEP, we have a setup of some low-cost sensors and AQMS and how we are calibrating it. So I'll discuss how we are calibrating it using multiple methods, and then briefly touch upon the merits and demerits of all these methods. So this is just an introduction to what air quality monitoring is. I'll not get into details, but this is, on the side we see a map of India where we have around 555 AQMS. However, it looks a lot, but if you see on the Bangalore scale, there are very few of them, and that is where a low-cost sensor can, low-cost sensor with good performance can help bridge the gap. Now, why do we need to calibrate the low-cost sensors? LCS manufacturers, they often use off-the-shelf sensors for PM2.5 and gases. Gas sensors typically use electrochemical sensors which convert the chemical concentration into electrical signals, which we can then use to calibrate invert it to concentrations. These sensors are often, calibrated, factory calibrated, and the conditions in which they are calibrated may get affected, may not work when they are deployed on the field. So user-defined calibration using reference-grade AQMS can actually give us reliable monitoring. Similarly, for PM sensors, they are based off light scattering principle, and as we do get concentrations from the sensors. However, again, to get accurate values, it is good that we calibrate it against PM values from AQMS. So these are going to be my discussion points. I'll briefly touch upon the methodology that we are using at CSTEP, followed by some calibration details about the calibration methods, and I'll show comparison of these different methods using for PM2.5 NO2, and then discuss about the merits and demerits of these methods. So this is a little crowded slide, but on the left, on my left, at least I can see that we have the at CSTEP, we have the INDICET facility where we have sensors from multiple, sensors from multiple manufacturers. They're co-located with an AQMS. We get the data. So for this study, I'm going to show the data that we have collected from January 20th January to 19th of March. So it's around 2 months. And we have multiple species. All of that goes into, we clean the data, we do some exploratory data analysis, and we also have the functional relationship of the dependence of different species on different other species. All that is used to create a test train data set. This data set then goes into different methods. So for example, linear regression, we perform in linear regression, we don't have hyperparameter tuning, but for others we do. We find the best generalized model. So because we have multiple sensors, we can also create a generalized model and also a sensitized model. From all the methods, the values of the correlation coefficients, MA and RMSE that we get, we then use to rank them, and we use the selected model for that particular sensor. Now, the calibration method, it helps, as I said, it helps convert the signal into concentration, and we are using reference grade AQMS. We are going to look at 5 different methods. There are 2 types: parametric machine learning method like linear regression, quadratic, and some non-parametric methods such as random forest, XGBoost, and support vector regression. To start with linear regression, it is one of the simplest and most effective. It basically tries to minimize the sum of squared errors. We get the parameters beta 0 and beta 1 that we can then use to predict or estimate other values. Quadratic regression, again similar to linear regression. However, we are also including, along with the variables itself, we are also including a combination of those variables, including square terms. It can, however, as the number of variables increase, we can see a sharp increase in the number of total, parameters that we are going to get. So we will build the model, see if that particular combination is significant or not, and drop the ones that are not significant. So that way we get a simplified, more simpler model. Both these parameters can then be used to estimate the values in the test set. For random forest, it's an ensemble learning method, so it creates multiple distant trees. And based on it again depends on the user defined parameters. We do hyperparameter tuning to find the best number of estimators. Based on the tree, when you provide it a new value, it will traverse to the tree to find which of the value it satisfies. And across all the multiple estimators or the number of trees, it will take an average value to give you the output. Similarly for XGBoost, XGBoost is similar to that. Again, build multiple trees. However, we get each of the leaf, the endpoint is assigned a value, and the output is essentially sum across all the leaf values. The last one is support vector regression. So support vector regression is basically fitting a kernel to the data with certain, we allow it to some amount of error into it, and in support vector regression also supports both linear and radial, so essentially also fit nonlinear data into it. So these are the 5 methods that I'm going to test on. These are some information about how we have done it. So both sensor and AQMS are located at CSTEP. The sampling period is from 20th of January to 19th of March, which is 2 months, and we have collected multiple species. We are taking for PM, we are taking 1 hour averages of the data, even though the sensor will provide you at every minute. And for NO3 and O3, we are using 15-minute average data. During the sampling, we ensured that at least 75% of the data for that particular hour is available, or for the 15-minute period is available. We try to clean the data as much as possible, and we split the data into 80-20 train test split. And I'll discuss the results for PM 2.5 and NO2 next. To start with the linear regression for PM 2.5, on the left you see that on the left is the manufacturer reported PM 2.5 value, and on the right you'll have the values that we have obtained using linear regression in this case. So you see for manufacturer calibrated values, the R values are around 0.7. We also get some similar values. However, there's slight reduction in the MAE values. followed by quadratic regression. There is slight improvement as compared to linear regression. The MAE values has further reduced. Similarly, for random forest, we see even further reduction in the MAE values and some improvement in the R values. Similar for XGBoost and support vector regression. So based on this, we find that the XGBoost method works the best, while linear regression not so much. Moving on to my second species, on the left we have NO2 concentration. However, the concentrations are the signals that we get from the sensor, so it's going to be in millivolts. And on the right we have the calibrated values, so linear regression calibrated values. We see that there's a good agreement between the NO2 concentration from sensor and AQMS. With a R of 0.85 for quadratic regression, which does include, it will consider the nonlinearity in the data. It improves even further. It increases even further for random forest, where the MAE values remain same as good as quadratic regression. For XGBoost, it is performing quite well, 0.94 with a very small MAE value. And support vector regression, again similar to quadratic regression. So we see that XGBoost again performs the best, followed by, the last one is like the linear regression. So to give an overview, we see that we are able to improve the results quite significantly using, let's say, XGBoost. However, like on the calibration data, it works fine, but when you try it on the on-field sample, or once the calibration period is over, when the season change, you'll see that XGBoost may not perform well. For more details, please refer to the poster of Dr. Nidhi Malik. The discussion points here are, we have two types of method, quadratic and, parametric and non-parametric. The parametric ones are quite simple, they're consistent over time. There are a lot of simple assumptions that they make. It is able to generally, do a better generalization, and we can interpret the results coefficient-wise to understand how well each of the coefficient is affecting the overall results. For non-parametric, they have very good performance. However, they're sensitive to change. There are certain overfitting risks, and interpretation is slightly difficult. It's not as straightforward, but we can use something like permutation importance to identify which of the variables contribute to the model sensitivity. So here I have a small graph of how, so this model was built for, this model is for random forest regression for NO2, and we see that if we randomly change the values of NO2, it is affecting the most, so the model performance will get poorer. It is followed by CO, so CO is the second most important coefficient in this, followed by temperature and O3 at the last. So this kind of helps us interpret. This also gives you a little room for some trial and error in terms of which variables need to be included and which to be excluded. The merits, again, linear regression is very simple, very easy to interpret, it's efficient to compute, so it can also be put on some IoT devices and stuff. It assumes linear regression, which may not work for all the species, and it is effective, it is sensitive to outliers. For quadratic regression, it helps us capture the nonlinear relationships. It again provides more flexible model as compared to linear regression, but again, as the number of variables increase, it can become very complex and may be computationally more intensive to compute. For the non-parametric methods, they have very strong performance. It can handle nonlinearity very nicely. However, interpretation sometimes becomes difficult, and it is sensitive to noisy data. You have to train the model and perform hyperparameter tuning, because there are a lot of bells and whistles that you can use to control it, and then it may not extrapolate well. So we have certain examples in the poster where you will see that it will not extrapolate well beyond the data in which it is trained. So thank you.
Next speaker is Mr. Mrinmoy Chakravarti, and he is a LIU scholar and PhD student in UBC Department of Mechanical Engineering and SERB UBC Fellowship holder. He is jointly supervised by Dr. Naomi Zimmerman and Dr. Amanda. He is interested in characterizing household sources of air pollution and its impact on human health and climate change. He focuses on developing tools for assessing energy and health policies in developing countries like India, using both numerical simulations and field studies. To study the cooking emissions and building characteristics, he has actively collected data from villages in India using low-cost sensors and portable sensors and surveys. This data is utilized to inform models and help evaluate the potential impact of household-level interventions for better and healthy living. I welcome Mr. Mrinmoy.
Thank you for the nice introduction. Before I start, I just want to express a vote of thanks to the ICAS organizers. They have been doing a phenomenal job. Thank you all who are present today. So thank you so much. Today I'm going to talk about the black carbon puzzle, I would say. I know most of us have been talking about low-cost sensors, PM2.5 gas sensors. However, I'm trying to focus on a particular pollutant, black carbon, which is a part of PM2.5. So those who are aware of black carbon is great, but those who are not, I'm going to give you a quick refresher. So what is black carbon? Black carbon is a component of PM2.5 pollutant, and which can constitute around 2% to 22%, 2% to 20% of mass fraction of the total PM2.5 mass that comes from different sources. Here, I'm glad that a lot of experts are talking about PM2.5 and looking into particulate pollution and building efficient models so that they can understand the levels of concentration that people are exposed to. However, BC or black carbon is something that I am mostly interested in working because there are a lot of issues that is related to black carbon. So what are the major sources of black carbon that we are aware of? Black carbon comes majorly from a process called combustion, where we burn any kind of fuel. Whenever the burning is not happening in a proper, proper or efficient process, and it becomes an inefficient combustion, and then we see that black carbon emissions are happening, and it's also called soot particles, if you have ever heard of. So in India, residential sector plays the biggest role in kind of emitting black carbon because of usage of household fuels, for example, the solid biomass fuels, which most of us, I guess, heard of it, and that is kind of prominent in the northern region and Indo-Gangetic plain, where we see a lot of burden of air pollution. So how black carbon impacts us? First is the climate impact, where we know that black carbon absorbs light, and that kind of perturbs the atmospheric radiation budget. And that causes a warming of atmosphere. And this is also considered as the second most important climate forcer. Apart from climate impact, this is also found to be a toxic pollutant, and there are like evidences where inhalation of black carbon-based particles can cause respiratory and cardiovascular diseases in age groups like children, where cognition and memory-related effects have been identified. The other aspect of black carbon influence is the local meteorology. For example, black carbon kind of contributes to a warming of local atmosphere, and that kind of hinders the cloud formation. And it can cause a lot of extreme rainfall in different regions. There are other like problems and that we face in black carbon, and there's a nice document that you can see at the backside of this hall, and a lot of other things have been mentioned. So I know this session is about hyperlocal air pollution action, but as I was kind of focusing on, this is not I'm working on, I'm kind of focusing on black carbon, hyperlocal black carbon pollution, and the action around that. So it's not just an air pollution we are looking into. The most important part is, for any kind of air pollution, is monitoring. So even though there are monitoring efforts, as we can see, but monitoring black carbon has not been prominent in different regions. So why does it happen? Because there are a lot of challenges in field monitoring. This pollutant is not so easy to monitor, and it is also expensive at times, and there are alternative methods that are recently being published and proposed, which can be a solution to such problems. In addition to that, it's not only about the pollution that we care about, it's also about the nexus, the connection between how household uses the different energies for their daily life, and that is something which is related to the emission of pollutant. So it's important that we need data collection from multiple domains, use different kind of methods so that we can capture the drivers that actually causes different levels of black carbon in household cases. So as we are talking about black carbon, and I have previously mentioned that household air pollution is kind of mostly what we are looking into, we need to measure in different microenvironments. By microenvironments, I mean particularly maybe in somewhere where people spend most of their time, like kitchen or in the living area. So that is an important aspect. And in addition to monitoring in hotspots, like outdoor locations where people spend, like come together or do like their regular social activities, we need to do that sort of monitoring. So finally, all these steps are, like all these knowledge bases required to build a mitigation strategy, and which is around the residential sector, and that kind of helps us generate policies and some guidelines and standards as focusing on the residential or other sectors. Also, I want to highlight about this policy brief on which Subbu, CSTEP, and the other groups have worked on. Is an excellent source of information, and then I recommend all of you to read and kind of get enriched about black carbon. So we did a field campaign, and kind of I try not always to look into quantitative way, but also to try to understand the livelihoods and the social life, what are the things that kind of causes this sort of scenario. So you can see that there is like daily cooking with solid biomass fuel. This is how these households are kind of spending time. And also you can see the open burning that is happening, and that happens is because of the space heating requirements, particularly during the winter season. And what it causes poor living condition and also the extreme exposure to such pollutants. You can see that the soot particles deposit all around the walls, and this kind of their everyday life they're spending. And also this after the outdoor space heating burning, and you can see the ashes are gathering. And these are like one or two instances, but these are pretty common in rural areas. So daily households activities like cooking, boiling water, space heating are kind of the drivers of all these activities and kind of causes the emission and kind of exposure to black carbon. This is mainly happening because of the reliance on solid biomass fuel, which is a cheap alternative, and also they have easy access to such fuels. In addition to that, these households does not have proper ventilation, and that kind of creates an additional impact on their livelihood. So this is something we have also studied, and not going to focus into that, but this is one of the important aspects. So this study is focused on Unnao, which is kind of at the center of IGP. There has been several discussions and references of IGP and looking into the rural sector, because this is something as comparable to the urban region in terms of the pollution. So our focus was actually into rural areas. We used low-cost sensor modules. However, I'm not going to talk about it. I'm going to talk about the black carbon, which is measured by microethylometer, and the model is MA300, which is kind of a newer version of that. And we looked into the indoor microenvironments and as well as the outdoor community monitoring. These are like two images where you can see that indoor and outdoor monitoring are done. Apart from that, we looked into the household and community survey. These are essential informations, and we tried to actually approach in a mixed method analysis so that we can understand the quantitative data that we collect with the qualitative data that supports the drivers. So one of the major factors, as I highlighted, is the energy usage, and that comes from the fuel usage of these households. So what we learned, so this image that you are seeing is an interesting aspect of household cooking. These are the ignition fuels that these family use to start their cooking process. Even though they are using solid biomass fuels, they use these fuels for starting off because they can actually burn pretty fast and then start the cooking process. So what we found that most of these households are users of solid biomass fuels, and I also identified there is a linkage between the solid biomass fuel usage with their activities. So most of these households are connected with agricultural activities, and they are actually associated with having livestock in their households. So that kind of elevates the access of these fuels, because these solid biomass fuels are kind of built upon all these major sources. So the cleaner fuel option is LPG, which is in India, and there has been a lot of initiative, and I'm absolutely grateful that these initiatives are there. However, we have seen that it's actually used as a secondary fuel source, and you can see it's a clean, it's not so clean, but like an example that I have captured during the field campaign. So you can see the family is cooking, there's smoke from the active usage of solid biomass fuel, but there is even though they are subscribers of LPG, they are not using it. And you can see the amount of smoke they're generating. So we could not sample here because of the amount of pollution it's generating. So we need to switch to other houses so that we can actually measure. And all these are kind of promoting the multiple fuel stacking, which has been identified in several studies as one of the major causes of continued usage of solid biomass fuel. So this is probably one of the complex plot that I have to share with all of you. So this is basically the diurnal variation of black carbon that we have observed in the two locations. One, the brown one that you are seeing is in the village or the outdoor level, and the black one is for the household level. To give you an idea, this location A and location B, these are two villages, and the peaks that we have observed are kind of driven by several factors, like what kind of kitchen they have, and we also identified that these are kind of closely associated with their daily activities, like what they're cooking, when they're cooking. And we also identified that the outdoor activities and the location of the monitor plays a important role in capturing the hyperlocal pollutant patterns. So these are all important insights that we have captured by monitoring in these locations. So these are some of the lessons that we learned. One of the most important aspects is looking into the decrease in black carbon concentration during the afternoon hours. That's mostly driven by the atmospheric ventilation because of the process of planetary boundary layer height and the wind speed. And that kind of led us to think about how we can use this sort of information in developing some actions. And from that, we kind of identified that we did some calculations and identified that if households want to transition from a traditional solid fuel-based cooking to somewhere in cleaner cooking, then an intermittent strategy could be applied. And in that case, an evening cooking could be a better option, where they can get lesser exposure because of the atmospheric conditions. I know we are short of time, but if you want to discuss more, I'm available. We can talk about that. Apart from that, we are also trying to look into the analysis using a nested box model. This work is almost completed, and we did some simulations by looking into different household parameters, what are the different kinds of energy transition pathways, and also what are the parameters, for example, the combustion process, the ventilation factors that are available for these households. And these kind of lead us to develop an actionable strategy for these households. In addition to that, I'm also interested in looking into the community literacy. This is one of the sessions that we did with the households and kind of letting them know that what are the practices that they can achieve, they can actually do in their daily lives so that they can achieve a better, healthy life. And we also did a community science with arts. This is one of my activity that I love to do, like photography. So I did a photography exhibition and tried to let the community know in different regions of the world to make them understand about the situations around the world. So my final thought is we need to not only simply monitor, we need to also think about how we can take actions according to different ways. This could be a smaller actions in a localized level or an individual level, but these are very important. So maybe something that we should think of after this, the India Clean Air Summit. I guess, sorry about that. These are some of the members whom I would like to thank, my professors, committee members, my lab members, and all the funders. Thank you so much.
I will welcome our last speaker, Dr. Satish Swaminathan. He will talk about unlocking the potential of hyperlocal data by introducing an agent-based framework for modeling air quality. He is a postdoctoral research fellow at the Clean Air Toolbox, Columbia Climate School. He received his PhD from Indian Institute of Technology, Madras in Chennai, and his research is focused on applying the IoTs and data science for hyperlocal assessment of the ambient environment through mobile networking. At IIT Madras, he founded and led a project for developing a framework for hyperlocal air quality assessment through mobile monitoring. His interest spans around Internet of Things, low-cost sensors, mobile monitoring, and urban mapping. Mr. Satish.
Good afternoon, everyone. I hope you're up. Okay, so this is Satish. I'm going to talk about how you can use hyperlocal data and for making insights. Right. So here are some of the questions that we are trying to answer, right? So what is the air quality at any given location? How much are people exposed to on a daily basis? How does one measure air quality at high spatiotemporal resolution? And can high spatiotemporal resolution air quality data, can it be described? Can you understand what's happening? Can you start explaining why one location is more polluted than the other location? What are the anthropogenic activities that are actually causing a particular locality to get more polluted than the other? And then finally, how do you start devising mitigative strategies? Now, I know across this room, people are trying to solve each of these questions. Each of us are trying to answer each of these questions. But is there a unified framework which allows us to answer all these questions in a sequential manner? Right. So there are three things that we want to do, or there are three parts of the solution. One, we need data at high resolution. Next, we need to model or start analyzing the data to get insights. So these are the three components, and today I'll be focusing mostly on the modeling and analysis part. Right, so data is the first problem. So for hyperlocal data, again, we need a lot of sensors. So here we went ahead and started collecting data using mobile monitoring. So the advantage of mobile monitoring is you get a lot of spatial coverage, and the potential for spatial resolution is tremendous. So we can start collecting data at 10, 20 meter resolution if you want with mobile monitors. Now, here is a schematic of how you would do mobile monitoring. So first, we have these low-cost sensors which we deploy on vehicles. And as these vehicles travel around, they start collecting data. Now, let's say I deploy them on auto rickshaws or taxis. Wherever these go, they start collecting data from there. And all of this data gets aggregated to the cloud. And once it's on the cloud, you have an opportunity to model, analyze them, and finally you get spatiotemporal insights. Now, here are some of the devices that we built in-house. So these are multi-parameter sensors again, and the fact that we are doing it in a mobile fashion, it also allows us to monitor not just air quality, but various other parameters which change with space and time. And so we have 3 versions. So the first version is a static monitor, which we also use for calibrating. Then we have these mobile devices which we deploy on 3 or 4-wheelers. And then you have the IoT mirror, which is essentially a mirror-like encasing in which the sensors are placed for 2-wheelers. Right, so the first part is collecting the data. How do we do it? So we did a pilot study where we deployed a single vehicle on a bus. And we ran that bus in an area, across an area of roughly 13 square kilometers. And this is the route that we took. So this was a part of Chennai. And this particular route was designed in such a way that it has various land use. So if you notice, there's a milk factory, there's an industrial estate, there's a school zone, there's also some residential area. And it's a 25-kilometer route, and the vehicle ran 24/7, obviously in shifts, and we collected data continuously for a period of 30 days. Now, once you have that kind of data, this is the kind of results or insights that you can get. So what you see here is the PM2.5 concentration across a single day. So on a typical day, how does air quality look like? Or PM2.5 concentration look like? And if you notice, there are different hotspots. The hotspot changes over the course of a single day. Sorry. Right. So here are some of the interesting insights that we found. And here, there's no analytics that was done. It's just raw data. We plotted it across time. So if you notice, location 1 is a milk factory. At midnight, you see nothing, which is standard. There's not a lot of sources. And then, coincidentally, between 3 to 4, so that's the 3:30 time mark, between 3 to 4, we notice a peak at location 1. So when we went back and looked at what was happening, we realized that that is the milk factory, and the morning batch of milk gets dispatched from the factory between 3 to 4. And when a lot of trucks leave from that particular location, so that got picked up by this data, by this study. And then between 8 to 9, we noticed that the school zone becomes more polluted because there's a lot of people who come to drop their kids, right? So that part becomes more polluted. So similarly, we found a lot of insights across different time, but yeah, I'll move on next. So once we have this data, what do we do with it? How do we get insights? So to gather all the insights that I just told you about, we had to get those insights manually. So we had to look at the data, we had to plot it, and then figure out what is happening. Now, could we develop a framework to actually understand what's happening? Now, there are modeling paradigms which are available, which can help us understand what's happening, and then there are 2 types of models. One is the theoretical model. I think in the beginning we were talking about, yesterday's session, we were talking about the chemical transport models. You have your Eulerian, CFD-based models, Lagrangian models. On the other side are your empirical models, which are purely data-driven. And we also had Albert talk about how they are not physics-based, so they're purely just data-based. The advantage is obviously, so each of them have their own benefits, merits and demerits, but the major flaw, a major constraint on the models is, the first one is computationally intensive. All your theoretical models are computationally intensive because you're trying to solve algebraic differential equations, right? On the other side, you have data-driven models which are easier to solve, are not computationally that intensive, but they are not generalizable, they are not transferable. So let's say I build a model for this location, I cannot use the same model for another location without having to retrain the model again. Now, so we wanted to come somewhere in between. We wanted to also bring in physics as well as the data-driven the capability or the potential of data. And that's where the agent-based model comes in. Now, agent-based model is nothing new. People have used it for various other applications. But we wanted to apply the framework of agent-based model for air pollution modeling. Now, what are agents? So what is this? This is a whole different paradigm of modeling. So agents are essentially entities, autonomous entities, which are capable of interacting with each other as well as with the environment. So now what you do here is you essentially look at an entire system that you want to model, and you discretize it into agents. So each locality, let's say a 250 meter or 100 meter buffer zone, becomes an agent. Now, the way this model works is it fundamentally solves a mass balance at each agent. So agents interact with each other to exchange pollutants. Now, how do they exchange pollutants? How do you determine how the interactions work? So there are rules. So these are rule-driven agents, and they are all autonomous in the fact that they will be able to understand what's happening based on some data along with a fundamental model that's built. And based on that, they will interact with each other to exchange pollutants. Now, the properties, and how do you define the interaction? The interactions are based on the properties of each agent. And each agent has a property which is associated based on their land use. So this is where data comes in. However, at the base, the physics is in the form of a mass balance. It's a simple mass balance. You have where you have the pollutants. The first part that you see over here is the autoregressive term, which essentially takes care of pollutant in the previous time instance. Then you have the so we call it background pollution, or this essentially talks about your source and sinking terms. And then you have whatever goes in and comes out of your agent. And this is the fundamental idea or the fundamental mass balance which gets solved at each agent. Now, we took the same example, we took whatever data we collected for that particular area. And so the first step is we need to define the agents, the bound of each agent. So we took the data that we had, and then we condensed all those hundreds of data points into 22 agents. Why 22 agents? It could be any other number. This is again a tunable parameter, but for some reason we took 22. And these are all equidistant, if you notice. So we took all the data and we said each agent has some data associated to it. Now the next step is you start solving that mass balance at each of these agents simultaneously. And with that, so we got a least norm solution for this particular, while solving that system of equations. And here, if you notice, so this is how at each agent, the model predicts versus the observed value. Sorry. Right. So if you look at this, the models are pretty much capturing what we observed in the temporal aspect at each agent or at each location. So for instance, location 6 is the location of the milk factory. And here you notice between 3 to 4 you have a peak. The model also captures a peak, but there is some deviation. But that I'll come to later. Now, how do you know that this model is even predicting something which is reasonable? How do you know that you can rely on this model? So we went ahead and tried to understand what the resultant parameters are actually associated to. So we believe that there are two basic terms. The BP term captures the source sinking part at each agent, and there is a transfer term, which is the K term that we call, which talks about how pollutants get transferred between one location to another location. Now, if you notice, the transfer coefficient seems to be highly correlated with the wind speed at that location across different hours of the day. So we took the aggregate wind speed at different hours of the day, and then we tried to understand how the transfer coefficient looks when compared against that. So that is the first part. The next part is we believe that because this is typically an urban locality, traffic has an important role to play in the emissions. So we went ahead and tried to understand how traffic density is affecting the BP, or is there any association between traffic density and BP. Since we don't have traffic density, we use the surrogate, which is traffic speed. So the inverse of traffic speed will essentially give you congestion. So if the traffic speed is really high, then you know that there's very little congestion. But if the traffic speed is low, And this is relative traffic speed. So you'll know that there is considerably lesser congestion. Now, so what are the things that you can do with this model? We believe that you can do descriptive analysis. Can you describe what is happening in that system? So if you look here, so these are all agents, and so the color coding is the change in BP from one time instance to the other, and all the arrows dictate the direction of flow or transfer from one agent to another. And if you notice at 8 a.m., between 8 to 9, you notice the agent near the school zone becoming really high. So that becomes a sourcing term. So you realize that that part has a source. Now, what else can you do? Can you start understanding which of these agents are source dominant and which of these agents are transport dominant? Can you say, oh, these locations are source dominant, or source is, or localized sources are a major contributor to the PM concentration, or are they coming from somewhere else? Are they transfer dominant? Now here again, we try to understand which ones are source, and so all the blue ones that you see are convective dominant, which essentially means the pollution change or the change in PM concentration at that particular location is dominated by transfer terms. And you see some which are BP dominant, which is the source dominant. And the other ones are, it's just very difficult to separate out which one is which. And then, can you use the same model for making predictions? So this is where spatio-temporal interpolation comes in. So typically when people talk about interpolation, they either look at the spatial aspect or the temporal aspect separately. But here is a framework which allows you to look at both of them together, because the agents are getting solved. So you're solving this mass balance across all the agents simultaneously in time. So that way, we found out, we just compared it with various spatial interpolation techniques and a couple of temporal interpolation techniques, and we found that the agent-based model seems to perform better. The same thing, can you do temporal predictions? Again, this is how the error keeps progressively going down over time. So over a period of 9 days, you'll notice that the RMSE value keeps going down. And this is how the model is capable of predicting in time as well as space. Next, can you use the same model for making prescriptive assessment? So exposure assessment, how do you do it now? So one way is I can either give each of you a personalized monitor, or we could use satellite data and then do time activity-based analysis. Now, if I have this agent-based approach, all I need is your location information, and then I essentially do an aggregation of time and the pollution at that particular agent, and I associate it with the location that you're at. Now, another simple application of that might be, so Google tells you which is the fastest route between point A and point B, right? Can I tell you which is the cleanest route between point A and point B? So this is one particular approach. So what we did was we essentially aggregated. So we took a particular route, and we said, which agents are covered in this particular route? And all you have to do at the end of the day is add the pollution at each one of these. You also factor in the time, and you also weigh in the breathing rate, mode of transport, and other stuff. But then you essentially have to do an integration or an addition in this particular case. And here you notice that there are some routes which are fast, but they're not the cleanest. Even though you spend lesser time in that particular route, there is a possibility that another route is least exposure route. Now, how do we bring in real-world parameters? So all the results that I showed you so far are not based, so we've not brought in real-world features at all. So that's just a system of equations that get solved, and the parameters that precipitate out of that system of equations getting solved. The next step is for us to parameterize the BP and K in terms of real-world features. So this is where, again, here we borrow the principles of land use regression, where we parameterize BP in terms of whatever could contribute to source. For instance, road width, traffic density, tree cover, for instance. And the K terms could be dictated by wind speed, wind direction, maybe, again, road width also, because you have tunneling effect and stuff. So you parameterize BP and K now in terms of the real-world features and fit them back into the original model. So once you fit them back in the original model, yeah, I'm done. So once you fit them back in the original model, you also integrate the real-world features with the fundamental mass balance. So to summarize, agent-based framework we propose for modeling hyperlocal air quality. And again, I'll just summarize, come to the last part. So we believe it can provide a unified framework for doing descriptive, predictive, and prescriptive assessment. Thank you.
Thank you, Dr. Satish, for your presentation. Now the floor is open for questions. Soumya.
Thank you, speakers. I have questions for Dan, and so I'll start with Dan. So, you know, now we are talking about the multi-pollutant sensor. So I just wanted to get your thoughts and comments on where are we with the ammonia. Do you think actually ammonia is important to measure, and are we? Is there anything happening in the sensor world for ammonia measurement?
Yeah, I think it's definitely important because it's a key precursor of PM 2.5, and especially where, you know, there's not a lot of sulfate, you can get ammonium nitrate aerosol in like agricultural areas. I don't think there's really a lot of good news in terms of sensors for ammonia, at least low-cost ones, but yeah, I'd probably defer to the sensor experts on that.
Okay, I'll ask I think I'm done. I'll ask the question later. Thanks.
Hi. My question is to Dr. Satish. So when we are looking at the model here, hi. Okay. When we're looking at the model, we're trying to solve a Lagrangian equation or a Eulerian equation when it goes to theory, and then there's data. When you're talking about agent-based model and you talk about mass balance equations being solved at particular agents, how is it that we're taking dispersion into account, or metrology and other factors as well? Do we take them into account, or how does that happen?
So as I said, the agents interact with each other to exchange pollutants, right? And then dispersion is actually taken into account by your transfer term that we have. So each agent can say how much, so let's say at each agent X amount of pollution gets generated, Y amount of pollution transfers. This Y can be split into what is coming in and what is going out. Now whatever comes in is from the nearing agents, right? So that's how the dispersion effect comes in, and whatever goes out again goes to the nearby agents. So that's how the dispersion model comes in. But I believe that the framework is what is more important. Instead of solving a mass balance, you could solve another complex differential equation at each agent. But that particular model essentially tells you how the agents interact. So it's a rule which defines how the agents interact, and it could be different. So for our case, we are using a simple mass balance.
Correct, correct. On those similar lines, if we are, let's say, talking about computationally being better, this agent model or the data-driven models, how much of a difference do we feel is there in between the three techniques that you were talking about?
So yeah, your chemical transport models are really complex because they'll take a lot of time and computational effort to solve for a smaller region also. On the other side, your data-driven models depend on how large an area you're covering, and at the same time depends on how many variables you're looking at. But with the kind of computational resources that we have right now, I think it's much more easier to do data-driven models when compared to doing computational transport-based models. The agent-based model, so when I told you about this mass balance gets solved, it's a system of linear equations. You're not solving differential equations here, it's just a system of linear equations. So it wouldn't take a lot of time. And the other side, when we bring in the real world features, it's almost the same as a land use regression model.
Okay, okay. So basically the complexity of the first part might change how the agent-based model computes the entire thing.
Correct. That is if you use a dispersion model or a complex model at the agent level.
Correct.
But if I use a simple mass balance, I think it's going to be...
Okay, one more question. When you're talking about the transfers between two different agents, dispersion effect coming into picture, we you talked about some rules of their interaction. So that's where we define all of that feature,
Correct.
right?
So in this particular case, that rule is the mass balance.
Okay. Okay, cool. Thank you.
Hello. Yeah, hi. My name's Rahul Burgese. I'm just an interested consumer of air pollution on a daily basis. So the use case you outlined was very interesting, and I was wondering if that's something that I guess obviously can be used by a company like Google on Google Maps for overlaying and actually making millions or billions of consumers aware of pollution levels and get more advocacy for a variety of things over time. Is that one of the things you see, or you see many? You must be having tons of other sorts of use cases which could be used for advocacy and building awareness and action.
Yeah, yes, so one of the potential applications is that Google or an Apple Maps or a Microsoft Bing Maps could actually use such data to inform end users upfront about which is the cleanest route. Obviously, there are other, so hyperlocal data has a lot of applications. So we believe that you can also do very localized mitigative action. So there's one work that we've done where we try to understand which locality, not even localities, I'm looking at street level, which streets are major sources of pollution. So can you take very focused, localized mitigative steps rather than doing a blanket policy for the entire city or for an entire state? Can you say, oh, these streets, there's something that has to be done. So for instance, let's say there's a hospital right next to a traffic junction, so in one of the localities that we were measuring, right next to the school zone is a heart hospital. Now, can you say I want to reroute traffic at that particular time alone? Now, this model will allow you to do that. So you can try different scenarios where you change, let's say, the traffic density at that particular location between 8 to 9, and you see how much the air pollution comes down by. Now, another advantage of such a model is that you can also start bringing in control frameworks, MPC, for instance, a model predictive control and stuff, to actually bring down pollution with some constraints. So yeah, I believe there are a lot of applications for this kind of data as well as the modeling approach.
Yeah, hello. I want to congratulate all the young panelists on the dais for your phenomenal work. I want to direct my question to Mr. Mrinmoy.
Can you please introduce yourself?
Hi, I'm Kiran Murthy. I'm from the University Vishweshwaraya College of Engineering in Bangalore. I want to direct my question to Mr. Mrinmoy Chakraborty. I want to know your thoughts on carbon capture and storage as a mitigation plan for black carbon.
Well, thank you for the question. To my understanding, carbon capture and storage is something which is related to carbon dioxide, not related to black carbon. So black carbon is basically a pollutant which is a part of aerosol, PM 2.5, what we are all discussing, and carbon capture, whatever. This is to my knowledge. If anyone would like to comment, please. So I guess this practice that you are talking is related to capturing carbon dioxide, which is a gaseous pollutant.
Any other question?
There's an online question. I think it's to Satish. How land, sea, breeze affected this study?
So this is somewhere in the interior of Chennai, and I'm not sure how much sea breeze affected because it's further in, it's inland. But yeah, the next step of the model is to actually look at the wind speed, wind direction, and if you notice the wind speed information, wind speed data actually associates very closely with one of the parameters. But we haven't done any analysis specifically on how land breeze or sea breeze affects PM 2.5 at that particular locality per se. But we believe there will be an effect, but it's too further inside, inland, for this particular data set.
Thank you. Hello everyone, I'm Shreyata. I'm doing my PhD from Indian Institute of Science. So I have two questions, one from Professor Dan. So it was a really interesting presentation, and I would like to ask you a question from the part where you mentioned that you have made a home-based sensor to monitor NO2 and TVOC. So I wanted to ask you that, is it formaldehyde-based sensor, and is it estimating TVOCs based on that, or there are some other volatile organic compounds that you have fundamentally considered while making that sensor?
Yeah, so thanks for the question. The TVOC sensor that we're using is a photoionization detector, PID. It's one of the higher sensitivity ones. I forget the exact electron volt number that it's used, but it's basically going to be sensitive to 95% of all VOCs, I would say. Anything that has like more than one carbon atom. So it's really not feasible to have selectivity of what specific VOC. I think our idea for it was we were going to use it to monitor a certain like fence line situation where we know that the massive amount of VOC in that area is a specific VOC, and that way we can just be like, okay, well, it's total VOCs, but most of it is ethylene oxide or something like that. But yeah, it doesn't really have any ability to select different VOCs.
Thank you, sir. Then next question is to Dr. Satish. So it was a nice combination of using the first principle and data-driven techniques that you have shown. But I would like to ask you a question that, have you considered all the possible variables? Because you discussed regarding 2-3 variables in depth, and I assume that you would have considered other variables as well while you were developing that model. So do you think that using this model or using this approach rather can be generalized or can be scaled up, since it's not just data driven, and can it be like also combined together with the temperature and humidity? Because if we are going to change the location, that is something which is going to impact the emissions a lot.
Yeah, thanks for the question. So the first answer, which is how many parameters or how many other pieces of information can you bring in, which is where I personally don't know what affects BP. So there are two parameters here. The main parameters are the BP and the K. So the BP talks about all the features, real world features that can affect the sourcing or a sinking capability of a particular location. Now this could be tree cover, this could be the presence or absence of water bodies, this could be just the roadway, traffic density. It could also be meteorological parameters. On the other side, there is also K, which will primarily be all the features which can affect the transfer, right? Or the convective part of it. I personally don't know which of these, which features will get parameterized under BP or K. Now here again, when we start using a regression model, ultimately we'll use a machine learning or some other regression model, where I'm going to be agnostic of how it gets parameterized. I'm going to give all the data that is possible, and I'm going to say, okay, what is the best combination, best weight of features that describes BP, which will ultimately fit the data, or will ultimately fit the ground truth, which is the measurements. So that is how we would solve this particular problem. And scalability wise, it again depends on how you define each agent. So right now in this particular case, each agent had a bound of roughly around 250 meters, 300 meters. I can do the same thing at a city level. I can say, how does Chennai, Bangalore, Hyderabad, Mumbai exchange pollutants? I can do it at a state level. It's just that the agent's domain will change. But the mass balance will still remain the same. And the features will also more or less be the same. The resolution obviously will matter. So let's say at this street level, we will need very high resolution, let's say wind speed or wind direction data, road density data or vehicle density data. But if I'm doing it at a state level, maybe I'll need lower resolution data for all of this.
But don't you think that temperature and relative humidity, which are very fundamental meteorological parameters, are going to affect
Absolutely.
it? So
They will be, which is why I'm saying they can get parameterized under BP or K.
right.
That will also be one of the features that we'll add.
Thank you.
Yeah, I have one question. How do you determine the distance? Like, okay, there is one source and up to some distance there is some sink. So up to what distance it will travel like that? In your case, it is equidistance, okay, but in real condition it might differ.
Right, so this is another sub-problem of this entire problem, which is how do you define the bounds of an agent? So here again, there are Voronoi diagrams, there are different kinds of technique where you say, what is that homogeneous space where the properties are consistent? So if I see a drastic change in properties, I can say, oh, now it's a new agent. So let's say there's one bound where the properties are more or less similar in terms of the road network or the road width, the traffic density and other features that we're talking about. And the moment I see a drastic change, I can say, oh, now it's a new agent.
Yeah, and one more question. Like in your notes, you are defining based on source, like somewhere coming from the industry or vehicular emission is potential. Okay, but in some point, there is sources coming from different sources actually, that in node. But there is some potential which is causing effect to other sink, let's say. But the strength or the amount of pollutant is also different. So how do you account for that?
So again, here we take in a lot of these land use features. So I don't know what is the strength. At the end of the day, I'm trying to put all those features into BP. And I'm going to say, oh, BP is all these features with these weights. Now, once I know the weights from the regression, then I know, okay, this particular feature is affecting BP, which is the most significant contributor to pollution at that particular location.
Okay, thank you.
Now we will wrap up this session. I would like to thank our speakers for their insightful presentations and the audience for their engaging participation. And let's consider how we can leverage these insights to drive meaningful changes in our communities. Thank you, everyone.